Welcome to another lecture of this course, Mathematics for Economics Part 1. So, the topic that we have been covering is called differentiation, as you can see on your screen, differentiation. We have been talking about the definition of differentiation, we talked about limits, and there are different rules of differentiation, we talked about them. Today we shall deal with another subtopic within differentiation. This is called partial differentiation. So, what happens in a partial differentiation? Remember, so far we have been talking about a function of a single variable. So, y is equal to f x. So, x is the only independent variable or explanatory variable of this variable called the dependent variable, which is y. But in economics we often encounter functions which have multiple independent variables, and if you have multiple independent variables, then each of these independent variables can change, and if they change, then what happens to the value of the function? How much does the value of the function change? So, that is what we are going to discuss today, which is the topic of partial differentiation. So, this is a technique to find out the instantaneous rate of change of the dependent variable with respect to one of the many independent variables, because there are multiple independent variables, and it is possible that some of them are changing. All of them might not be changing, maybe just one of them is changing or two of them are changing. Then how does the dependent variable change? What is the instantaneous rate of change of the dependent variable? So, those things are the subject of today's talk. Okay, let us go to the particular portion. Okay, so, this is what we are going to deal with today, partial differentiation. Functions of more than one variables. So, a function f of n variables, n could be any number, and these variables, let us call them x 1, x 2 and x n. So, there are n number of independent variables, and they belong to this particular set D. Remember, this is the domain set. So, this function f is a rule that assigns a specified number f of x 1, x 2 dot x n to each n vector x 1, x 2 dot x n in the domain capital D. Right, as we know, a particular function is a rule which assigns a specified value of the dependent variable for a particular value of the independent variable which belongs to the domain. Here, instead of one independent variable, you have n number of independent variables. So, you have a particular vector x 1, x 2 dot x n. With respect to this particular vector, you get a value of the dependent variable, which we are denoting as f of x 1, x 2 dot x n. So, to fix our ideas, I start with an example. An example of a function with multiple variables from economics is the Cobb-Douglas function. Okay. So, this is a very well known form of function in economics, often used. This is called Cobb-Douglas function, and here we are dealing with a particular Cobb-Douglas function. This is called the production function. We have encountered production functions before. Here on the right hand side you have the level of output, which is denoted by capital Y. It is a function of, in this particular case, two independent variable L and K. L is the amount of labor and K is the amount of capital. So, these are the usual conventional notations we use, capital K for capital and capital L for labor used in the process of production, and labor and capital are used and combined and we get a certain level of output, which is denoted by this function. And in this particular case, look at the form of the function. First we have a constant, here it is 2.30, then multiplied by L to the power 0.7 and K to the power 0.3. So, both L and K have their powers, and these powers in this particular case both of them are less than 1. Okay. And you can see that if L and K change, then Y will go on changing. If any of them is equal to 0, then the level of output becomes equal to 0, because of the fact that both of these inputs are indispensable, right. You cannot put 0 amount of labor and expect to produce any level of output with the help of capital alone. So, that is not possible. So, that is why this form is taken. Like single variable functions, here the domain consists of those values of the independent variables for which one gets meaningful values of the function. So, remember, in case of a single variable function, we said what is the domain. Now, domain, if it is not specified otherwise, it will consist of those values of the independent variable which give you meaningful values of the dependent variable, or which makes sense. In this particular case, for example, L or K cannot be negative, they could be positive, they could be 0, that is fine, but unless it is specified L and K, we can assume they cannot be negative and they should be minimum 0, but can go on increasing as far as possible depending on the ability of the producer or the availability of resources. So, that is how the domain is defined. Here is another example of what is known as the utility function. Here U is denoted on the left hand side, which represents the utility a person gets, and you can say on the right hand side you have a particular expression A1 ln. I have not discussed this log, this particular term before, which we shall deal with later on, but this is called natural log ln. For the time being, it will suffice for us to note that log or natural log is defined only for positive values. In the minimum they can be 0 and they cannot be negative. So, log of a negative number is undefined. So, in this case you have log of x1 minus c1 plus a2 multiplied by log of x2 minus c2. The values of xi's must be at least equal to ci, because if ci is less than xi, only then the value inside becomes positive, right. At the most ci can be equal to xi, which will give us a 0 value. Log of 0 is also somewhat problematic, but obviously ci cannot be more than xi. So, therefore, here this function is defined only if xi is greater than ci, or in the minimum xi can be equal to ci, right. So, what are xi's? Xi's are the values of the goods that a particular consumer consumes. So, xi is the amount of good xi which the particular consumer consumes. So, in this case xi has to be greater than or equal to Ci. That basically can be interpreted as Ci is the subsistence requirement of consumption of a particular good. That basically means that suppose you are an individual, you will need certain basic amount of food, for example, to survive. So, your food consumption cannot go below a certain level, otherwise you will not be able to live. Therefore, you have this kind of function which basically captures the fact that consumption cannot be below a certain level. Okay. Now, we are talking about 3 variables here, remember at least 3 variables, because 2 variables are independent and 1 variable could be dependent. Number of independent variables can become more than 2 also, but in the least they can be 2. Geometrically, here you have a 3-dimensional space. In 3-dimensional space, functions such as x is equal to a or y is equal to b, they represent planes parallel to yz plane and xz plane respectively. So, here is an example. So, instead of a, I have taken suppose x is equal to x naught. Okay, how does it look like? What does it represent? So, in this 3-dimensional space, suppose this is the value of x 0, right, and x should always be x 0, which means you have a plane sort of wall kind of structure at x is equal to x naught. So, x is equal to x naught represents any point on this wall, right, because on this wall the value of x is fixed. Similarly, here you have value of y fixed, and remember this y is equal to y naught. It is also a wall and it is parallel to what plane? It is parallel to this yz plane, right. Similarly, your x is equal to x 0 is parallel to this yz plane, and this is parallel to xz plane. And if you take z is equal to z naught, so the z coordinate is fixed, then you have another plane which is like a kind of roof, and along the roof you have z which is always fixed, and this roof is parallel to x y plane, right. So, this sort of equations such as x is a fixed number, y is equal to fixed number, z is equal to fixed number, they are actually planes parallel to the z y plane, parallel to the x z plane and parallel to the x y plane respectively. So, and now we let us talk about a more complicated sort of plane. Let us talk about this x multiplied by p x plus y multiplied by p y plus z multiplied by p z is equal to c. This is what we are calling as the budget plane. Why we are calling it the budget plane? Remember when we were talking about only 2 goods, right. Suppose x and y were the 2 goods, then we talked about what is called the budget set and the budget line. Remember this was x, okay, and you had x p x plus y p y is equal to suppose c. C is the income. Okay. So, this is 2 dimension, but if you have 3 dimensions, so 3 goods are being purchased, right. Then you have another term. So, you have x p x plus y p y plus z p z is equal to c. So, your total income is getting subdivided among 3 goods, right, and you are spending your total income. Then geometrically, how do we represent this particular equation? Well, here it is not a straight line, it is basically a plane in the 3 dimension. So, this is the plane that we are talking about. It is a triangular plane which is having some point of intersection with the 3 axes, and these are the points of intersection C divided by p x 0 0. So, this is that point, suppose this is A, this is B, this is C, right. So, A represents this point, B represents this point, and C represents this particular point 0 C divided by this should be P z, not P x. Okay. And we know that this is obvious because suppose you are talking about point A, here the person is not consuming any y and z, the entire money income is being spent on x only. So, how much x can he buy? He can buy C divided by P x. So, that is why the coordinate of point A is C divided by P x 0 0, likewise for the other 2 points. And these are the corner points, but inside if you look at the interior points, they are having positive values of all the 3 goods, right. So, it represents all combinations of goods x, y and z which a consumer can buy if the prices of these goods are p x, p y, p z respectively and the income is C. So, this is one equation. Now, we talk about a more complicated equation. Here you do not have power to be 1, but here now we have squares, that is the power is 2. So, suppose you take this particular equation x square plus y square plus z square is equal to k square, and we are saying this is the equation of a sphere with k as its radius. So, remember again, if you had x square plus y square is equal to k square, then we have seen this is the equation of a circle. I am sorry. So, this is k, the radius is k. So, this is your x axis, this is your y axis, and this is the circle. Right. But now you have a third element z square, and we are claiming that from a flat circle we go to a 3-dimensional sphere. So, this is how it is going to look like. You have x axis along this x, and you have y axis, and here along the vertical direction you have the z axis, and you are saying that this is k. So, here the equation is x square plus y square plus z square is equal to k square. Okay. Now, what is the argument why we are claiming that if you have this equation, then the corresponding figure or graph in the 3-dimensional plane will be a sphere. This is because x square plus y square plus z square is equal to k square represents the collection of all points which maintain a distance of k with the origin 0 0 0. Okay. So, this is easy to see that you take any point on the surface of the sphere, right, on the sphere, and you think about the distance of that point from the origin is 0 0 0, then one can show that this distance is equal to root over of x square plus y square plus z square, right. And what is this distance after all? It is the radius. So, if you take the squares of both sides, so therefore, you have radius square is equal to x square plus y square plus z square. So, therefore, you have this equation. So, that is the demonstration. Now, from the equations of equations in 3 variables which are represented by different shapes, we now come to what is called a function, right. Remember, there is a difference between a mild difference between equation and a function. Now, we are talking about a function, suppose. So, you have a function z, which is a function of two variables f of x y, and the graph of the function would be a surface in the x y z space. So, suppose you talk about this particular, which is represented on the left hand side, right, the graph here. Here you have a surface, it looks like a funnel kind of thing, right, and if you talk about the equation of this kind of funnel, it could be like z is equal to x square plus y square, right, and you can add some constant with coefficient of x square, coefficient of y square, but this could be a general shape, and this shape is called a paraboloid. Okay. From the word parabola, because if you recall, the shape is this, right, y and x. So, this is 2 dimension. So, instead of this you have now this. So, z is equal to x square plus y square, and you have this sort of surface, no longer a curve. So, this generally is called a paraboloid from the word parabola. For the time being, ignore the figure on the right hand side. So, what we are saying is that if you have z is equal to f of x and y, so you have the dependent variable to be a function of two variables, then one can represent this function in the 3 dimensional space. I have taken a particular form of function, and this form of function will give us this kind of shape, and it is called a paraboloid. Now, for a given value of z, we can define what is known as a level curve. Okay. Level curve means what? For the function z is equal to f x y, one can define a level curve for, suppose z is equal to c, c is a constant. Okay. So, the level curve will have this kind of equation, f of x y is equal to c. Notice this equation is a equation which involves only two variables, right, only x and y, it does not involve z. So, the plane z is equal to c intersects the graph of z is equal to f of x y. The intersection, when projected on the x y plane, gives us the level curve f of x y is equal to c. So, that is the full explanation of this. So, first you start with this function z is equal to f of x y. So, correspondingly we will get this kind of surface, right, a paraboloid. Then you take z is equal to c, c is a constant. So, here is perhaps one example, suppose this is c, right, this height is c. So, this z is equal to c is actually a plane, right, as we have seen, it is a plane parallel to the x y plane. So, this z is equal to c plane will intersect this paraboloid, right, and from this intersection, which in this case looks like a circle, we basically project this on the x y plane. So, this is how the projection is being done. Okay. And this projection, when it is done on the x y plane, we get this level curve. So, on the right hand side you have this level curve. So, for different values of c, you will get different level curves. For example, here z is equal to c, but if you could take a different value of c, right, and the projection will also be different. So, there will be a different level curve. So, that is why you have on the right hand side different circles. So, here the level curves are all circles in this particular example of a paraboloid. All the level curves are circles on the xy plane, and they cover all the 4 quadrants, you can see that. Okay. So, that is what I have written, the plane z is equal to c intersects the graph of z is equal to f of x y. The intersection when projected on the xy plane gives us the level curve whose equation is given by f of x y is equal to c. So, here I have just written what I have just shown you. Imagine the level curve of the function z is equal to x square plus y square. The function yields a surface which is called a paraboloid. Here on the left hand side you have the paraboloid. The level curve is given by c is equal to x square plus y square, and as we know x square plus y square is equal to c. It is the equation of a circle in the xy plane. And what is the radius? The radius is root over c. As c is rising, you have different sorts of level curves. This was a general discussion about level curves. Now, we come to particular discussion in economics. So, here you have y is equal to f of L k. Remember, this is the general form of a production function of 2 independent variables, labor and capital. Below is the graph of a Cobb-Douglas production function. So, here you have sort of starting from 0, this is the origin. Vertically you are going up, that is the output level, and it is color coded, which means that if you are going along the same color, the output level is remaining same. So, you can see these lines here on the surface of the curve, and on the surface you have these lines, right, and these lines are level curves. As you are going up, the color is changing from blue, it is changing to red, which means that the output level is rising, right. So, greater and greater level of output as you are going to the shades of red. The level curves of this function are called isoquants. So, isoquants are given by this equation, c is equal to f of L comma k, where c is a constant. So, on the 2 dimension, so if you draw that, because we know the level curves are projections on the 2 dimension. So, in this case the projection will be on the L k plane, so labor and capital plane. So, you will have this sort of downward sloping functions which are convex to the origin, right. So, these functions are parallel, all of them are convex to the origin, these are called isoquants. It represents all combination of labor and capital that produce the same magnitude of output C. So, that is the interpretation of this. It is not difficult to understand, because that is what we are getting here, right. So, along the level curve the output level is same, but different combinations of labor and capital are there. So, isoquants therefore represent different combinations of labor and capital which produce the same level of output. So, an example of a production function. So, you take this particular Cobb-Douglas production function, y is equal to capital A multiplied by L to the power alpha, k to the power beta, and alpha and beta both lie between 0 and 1, not taking the value of 0 and 1, and alpha plus beta is less than 1, right. This could be a particular production function. From this, if we draw the isoquants, then the isoquants will look like this, downward sloping lines, and they are moving away from the origin as they are going down, which basically means that they are convex to the origin. Okay, now from 2 dimension we come to n dimension, the general case. In the general case of functions of n variables, the set of all possible n tuples of real numbers is called the Euclidean n dimensional space or n space. This is denoted by R n. Okay. So, just imagine that we talked about 2-dimensional space which was R 2, we talked about 3-dimensional space R 3, but suppose instead of 2 and 3 I take a general n, right. So, that will also be an n-dimensional space. So, this is called Euclidean n-dimensional space or n space, and this is denoted by R n. Suppose you have a function which is z equal to f of x 1, x 2, x n is a function of n variables. The graph of f is the set of all values x 1, x 2, x n, comma f of x 1, x 2, x n, right, and this will be in what space? It will be R n plus 1 space, for which x 1, x 2, x n belongs to the domain of f. Obviously, if we are talking about a function, then the independent variable has to belong to the domain. The graph is called a surface or a hypersurface in R n plus 1. So, this is just a parallel of what we have seen before. So, here you had a paraboloid which was also a surface, and here you have a sort of dome kind of shape, right, for a Cobb-Douglas production function, but that dome is itself a surface, like a tent kind of surface. And now we are saying that for a general case this is called a hypersurface or a surface in general. For z is equal to c, a constant, the set of points in R n satisfying this f of x 1, x 2, x n is equal to c is called a level surface in level surface of f, right, level surface of f. We are not saying that it is a level curve, right. If it is a curve, then we are saying that it is in 2 dimension, but it could be more than 2 dimension. Therefore, we are saying that this is a level surface of f. Okay. So, this is the general form of a level surface. In the theory of the firm, the level surface, this f of x 1, x 2, x n is equal to c is called an isoquant. So, for the isoquant, the name does not change. If you have 2 inputs, it is called an isoquant. In that case, it is just a curve in a 2-dimensional space. But if you have multiple more than 2 inputs, then also it is called an isoquant. Iso means equal, quant means quantity, isoquant means equal quantity, because the output remains the same along the isoquant. Now, we come to the actual discussion of partial derivatives. So far, we were just building the blocks, we were gathering the building blocks of partial derivatives. Partial derivatives for a function of the form z is equal to f of x y. So, you have just 2 independent variables. We may want to know how quickly the dependent variable changes with respect to change in each of the independent variables. So, x might change, right, without any change in y, but if x is changing, then z will change. So, we want to find out what is the rate of change of z. The partial derivative of z with respect to x is denoted by this delta z delta x, or f dash of x x y. This is another way to denote the same thing, or f dash of 1 x y. Why 1? Because x is the first variable, or more explicitly f of x x y. These are all denoting the same thing, which is the partial derivative of z with respect to x. It measures the change of z or f of x y when x changes while keeping y constant. So, this is the interesting thing to note, that when we are taking the partial derivative of a function with respect to a particular independent variable, we are assuming that the other independent variables do not change. So, this was partial derivative with respect to x. Similarly, partial derivative of z with respect to y will be denoted by this del z del y, or f dash y x y, or f dash 2 x y, or simply f subscript y x y. It measures the change of z or f of x y when y changes, when the first variable, that is x, is held constant. So, here is an example. So, you have been given a function f of x y is equal to x y divided by x square plus y square. We have to find out what is del f del x and del f del y. So, to find del f del x, I use the quotient rule, right, because you have a quotient here x y divided by x square plus y square. So, we know how to do that. I take the square of the denominator in the denominator, and then the denominator multiplied by the partial derivative, right. Here is the important thing, you have to take the partial derivative of the numerator with respect to x minus the numerator multiplied by the partial derivative of the denominator with respect to x, and the rest is just simplifying this particular expression. And if we do that, I will arrive at this expression, which is y cube minus x square y whole thing divided by x square plus y square whole square. Similarly, the function is symmetric. So, if you have this should be y, if you have del f del y, then this should be the corresponding expression. For production function y is equal to f of L k, the partial derivatives are the marginal productivities of labor and capital. Okay. So, this is like the marginal productivity of labor when the production function was taken as a function of a single input. We have done that before, but now suppose both the inputs can change, then you have marginal productivity of labor is equal to the partial derivative of f with respect to L, and marginal productivity of capital is partial derivative of f with respect to k. So, here is an example. For the fishing industry, the production function is given by f of k L is equal to 2.65 k to the power 0.45 L to the power 0.4. So, this is a typical Cobb-Douglas production function, where k and L are capital and labor. Show that k multiplied by f dashed k plus L multiplied by f dashed L is equal to z multiplied by f for a certain value of z. Here f dashed k and f dashed L are obviously partial derivatives of f with respect to capital and labor. So, let us first find out the left hand side, that is, I have to find out the partial derivative of the production function with respect to capital. So, I simplify this and I get this expression 1.19 multiplied by k to the power minus 0.55 multiplied by L to the power 0.4. Similarly, the partial derivative of the production function with respect to labor will be 1.06 multiplied by k to the power 0.45 multiplied by L to the power minus 0.6. And then I try to find out what is the value of the left hand side. Left hand side is k multiplied by f dash k plus L multiplied by f dash L. So, I substitute these values that we have found into this expression and I simplify, and I get this 2.25 k to the power 0.45 multiplied by L to the power 0.4, and I can express this as this, right, 0.85 multiplied by the production function actually. So, we have basically proved the thing for z is equal to 0.85. So, the proposition that was supposed to be proved is correct if z is equal to 0.85. Like production functions, utility functions with multiple goods can be partially differentiated with respect to each good, and one obtains what are known as marginal utilities of goods. So, you have suppose y is equal to a is a constant x to the power alpha, y to the power beta, where x and y are the goods or the quantities of the goods the consumer is consuming, then you can find out what is del u del x, del u del y. These will be marginal utilities. Okay, finally, we talk about the geometry of partial derivatives and we talk about what are known as tangent planes. For a function of this form z is equal to f of x y, take a particular point x 0 y 0, the corresponding value on the function will be f of x 0 y 0, right. So, if you take z is equal to f of x y, you basically have a surface, right. So, here take this for the time being, ignore the plane which is the tangent plane, concentrate on this particular blue surface that you have got. So, you have basically from this point particular value of let us say x 0 and this is let us say y 0. So, you have x 0 y 0 at this value and at this point on the x y plane, and z of f of x y will give you a particular value of z and you are reaching here, right. So, this is the value of z, z is equal to f of x 0 y 0. So, that will be equal to z 0 suppose. Imagine a plane y is equal to y 0. This plane will have an intersection with the function f x y. Let us call the curve as c of y. So, suppose here y is equal to 0 and y is equal to y 0, we know it is a plane, right. So, you have basically a kind of wall kind of structure here, and this wall is going to intersect with the curve or with the surface, that is z is equal to f of x y, and that intersection is called c y. Okay. So, here is basically the c y, this curve is called c y, right. Y is equal to y 0, this plane will have an intersection with the function f of x y. Let us call the curve as c y. Imagine the tangent to c y at the point x 0 y 0. Let us call that this should be f of x 0 y 0. Let us call it as t y. Okay. So, you have this c y and imagine the tangent, there will be a tangent to this curve at point P, and this tangent let us call that as t y. The partial derivative of f of x y with respect to x at the point x 0 y 0 is the slope of t y. Okay. So, you have got this line t y, the slope of this t y is the partial derivative. So, this is f x evaluated at x 0 y 0. So, slope of t y is equal to this. So, this is the geometry of the partial derivative. What does it mean when you say partial derivative geometrically, right? This is what it means. Now, this is partial derivative with respect to x. What about partial derivative with respect to y? For that, what we need to do? We need to do a similar thing with x is equal to x 0. So, you can have a plane x is equal to x 0 and similarly a curve, right, c x, and similarly a tangent t x. The slope of t x is the partial derivative of f x y with respect to y. So, if you take x is equal to x 0. So, suppose this is x 0, then here you can imagine similarly another plane x is equal to x 0, and that plane will have an intersection with this surface, and that surface will be that curve will be C x, and similarly you will have a tangent which is T x. Now, slope of this T x is like before, slope of this T x will be the partial derivative of this function with respect to y evaluated at x 0 y 0. Now, these two tangent lines T x and T y, so this will be T x and T y, lie on a unique plane. This plane is called the tangent plane. So, this is T x and similarly here is T y. So, they both of them lie on a particular plane, and that plane is called the tangent plane. So, this is visually shown here. This plane that you are looking at is the tangent plane at particular point, that particular point is P. So, this tangent plane passes through the point A, x 0 y 0 f of x 0 y 0 in the x y z space that we have seen, right. It passes through this point P, which we are calling it as A in our text. The tangent plane is tangent to the surface at this point capital A. If we denote z 0 is equal to f of x 0 y 0, then the equation of the tangent plane at x 0 y 0 z 0 is given by this. So, this is the equation of the tangent plane. Z minus z 0 is equal to x minus x 0 multiplied by f dash of 1 x 0 y 0 plus y minus y 0 multiplied by f dash of 2 x 0 y 0. So, f dash of 1 and f dash of 2 are the partial derivatives of the function with respect to x and y respectively. Just think about it a bit and compare this with the two dimensional case. There also you had the equation of a straight line, right, where you knew the slope of this line, right, derivative, and you knew that it passes through x 0 and y 0, and there what was the equation? It was y minus y 0 is equal to x minus x 0 multiplied by the derivative, which we can write as m. This is the derivative or the slope, okay, at this point x 0 y 0. So, this is just a generalization of the case in case of 3 variables, and it could be generalized further if you have n number of variables, then it could be extended to that case as well. So, here I think I shall stop the discussion of partial derivatives. In the next lecture I shall start with something new. Thank you and have a nice day.